Okay, now I want to look at one application of two-dimensional vectors, and that is force vectors. Force vectors. All right, so we'll start simply, and let's assume we have an object at this point here, and then multiple forces act on the object at the same time. And we want to figure out what the result of all of those forces combined is on that object. So let's say, and I don't have a grid here to work on, so just bear with me. Let's say we have a vector that is, I'm going to use dots to indicate what I'm doing here. So let's say force 1 is 2 units to the right and 1 unit up. So this is vector F sub 1. Force 1. So vector F sub 1 acts on that object. You can imagine what would happen if that force was applied to this object, the object would move that direction, okay? And the magnitude of this force would kind of determine how far the object goes and things like that, all right? So that's force 1. Let's do 2 more vectors. Let's say the next vector applies a force that's 3 units to the right and down 2 units. All right, so it looks something like this. So that's force 2, F sub 2 vector. And then we have one more vector that, let's keep it pretty simple. Let's say it applies a force 4 units to the left. 4 units to the left. And we'll call this F sub 3. So what we might want to do now is calculate the result of all of those forces acting on the object. And so what that's called is, let's calculate the resultant force on the object. And let's, just so we can reference where the object is in our drawing, let's call this point P, right? So calculate the resultant force on the object at point P, all right? Let's be clear. And so, very simple thing to do, if you want to know what happens when you apply all of these forces, you simply add the forces together, all right? So what we need to do is figure out what these forces are as vectors. So let's describe F sub 1 in component form. So F sub 1 has a horizontal component of positive 2 and a vertical component of positive 1. F sub 2 has a horizontal component of positive 3, a vertical of negative 2. Finally, F sub 3 has a horizontal of negative 4 and a vertical of 0. So the resultant force, which we will, let's call it just capital F, so that's the resultant force, will simply be the sum of these forces 2, 1, 3, negative 2, and negative 4, 0. And so to add vectors, you simply add all the horizontal components and all the vertical components. So 2 plus 3 is 5. 5 minus 4 is 1. And then 1 plus negative 2 is negative 1, plus 0 is negative 1. So the resultant force is this vector 1, negative 1. Okay? So if you were to look at that in this diagram, it would be right 1 and down 1. So this is the result. This is the force that's applied on the object whenever you look at all of these being applied simultaneously. So not too much, and that makes sense because, for example, the downward force of F2 cancels out the upward force of force 1, and now you actually have a slight downward force. And you can see the resultant force has a slight downward force. F sub 3, the leftward component of f sub 3 cancels out the rightward components of f1 and f2 almost completely. So altogether you had a horizontal component of 2 and of 3, which is 5. So you're taking away 4 of those, leaving behind only one unit to the right when you're looking at the result of those forces. Okay? So that's how you calculate a resultant force. Let's look at another example. Let's say that F1, force 1, has magnitude. Let's give it a particular force now. So let's say force 1 has a magnitude of 5 pounds, right? That's how much force is going to be applied for this vector. F sub 2, sorry, these are vectors. Let's label them as such. F sub 2 has a magnitude of 8 pounds, let's say. They act on an object at Q, let's say point Q, as shown. So here we go. So here is point Q, and I will tell you that F sub 1 is looks something like this. Okay, F sub 1 looks something like that. And then F sub 2 has a magnitude of 8 pounds, so it should be longer. And it looks something like that. And then I will tell you that F sub 1, if you were to look at basically a positive x-axis, the angle to F sub 1 is, let's keep it simple, let's say that is 30 degrees. And the angle from the positive x-axis to F sub 2, let's say that is, we'll keep that simple as well, let's say that's 150 degrees, all right? So these two vectors, we know their magnitudes, 5 pounds and 8 pounds. We know their directions. They're acting on an object at point Q. Let's do two things. So part A, let's calculate the resultant force. So slightly different setup than the last problem. So now, the idea is simple, right? We just have to add the vectors together. But we need to know what they are, what the vectors are in terms of components. So F sub 1, if I were to look at F sub 1, it would look something like this, where this is 30 degrees, and its magnitude is 5 pounds. Okay, so 5. So that would mean that my horizontal component right here would be 5 times the cosine of 30 degrees. You can do that in your calculator if you want, but it happens to be 5 times the square root of 3 over 2. So 5 square roots of 3 over 2. And the vertical component would be the hypotenuse 5 times the sine of 30 degrees, which is 5 times a half. So that's 5 halves. So F sub 1, maybe you can't see that. Maybe that's off the screen there. F sub 1 equals the vector. Horizontal is you're moving to the right, 5 times the square root of 3 over 2. And you're moving up 5 over 2. So that's the F sub 1 vector. Let's do the same analysis for F sub 2. So F sub 2 looks something like this, where this angle is 150 degrees, meaning your reference angle here is also 30 degrees again. Magnitude of 8 this time. So it's important that you understand the horizontal is left, so that's a negative horizontal. So you take 8 times the cosine of 30 degrees to get the horizontal side, the adjacent side to 30 degrees. The cosine of 30, we already said, is the square root of 3 over 2. So you've got negative 8 times the square root of 3 over 2, which is just negative 4 square roots of 3. The vertical component is up, so it's positive, and it's going to be the hypotenuse 8 times the sine of 30 degrees. The sine of 30 degrees is a half. 8 times a half is 4. All right? So now we know vector f sub 2 is negative 4 square roots of 3, comma, vertical component 4. All right? So let's erase the drawings that helped us find our components. And let's calculate the resultant force. Let's call it F again. So F is simply going to be the sum of those two vectors. So you're going to have a horizontal component of 5 square roots of 3 over 2 plus negative 4 square roots of 3. So let's just say that's minus. So that's your horizontal component, comma your vertical component would be 5 halves plus this vertical component of 4. And if you wanted to round that to decimals, you could put those numbers into your calculator. Don't write equals, however, write approximately. So I'm going to type 5 square roots of 3 over 2 minus 4 square roots of 3, and it looks like that's about negative 2.6, comma, 5 halves plus 4, well that's 2.5 plus 4, so that's 6.5. So the resultant force acting on the object at point Q is this. If you draw it in the picture, you're going to go left 2.6 and up 6.5. That makes sense. Both of these vectors are going up, so they're just going to stack on top of each other and have even more of an upward force. This vector points more left, so it's going to counteract the rightward component of f sub 1, and it's going to leave behind a little bit of a left component, so that's the negative 2.6. All right, so that's the resultant force, negative 2.6 comma 6.5. Part B. Part B, let's leave our answer there for the resultant force. Part B, what force would be required? What force would be required to attain equilibrium? So equilibrium means that all of the forces together, so we'd have to introduce another force in this picture, so that all of the forces together would do nothing to the object, right? They would cancel each other out. So equilibrium means everything adds to nothing, which is the vector 0, 0. So if I want to know an additional force required to attain equilibrium, that means I would have to have another force that cancels the result of those two forces. So it's very easy to see that the answer would be positive 2.6, negative 6.5. If I add those together, I get 0. And so this force, in addition to those two forces, would result in equilibrium. And that's all there is to determine what you would need to attain equilibrium. And that's all about force vectors.